Hello everyone, this is Monica Lupion and today's presentation is about convective heat transfer coefficient. We will learn how to make an estimation of the convective heat transfer coefficient considering different conditions. This is the context of my presentation. First, I will review some fundamentals in convection, like for instance the difference between natural and forced convection. Then I will define very useful parameters that will help us to make an estimation of the convective heat transfer coefficient. Then we will study 4 different methods to make an estimation of the heat transfer coefficient. First, the dimensional analysis, then the exact analysis of the boundary layer, followed by the approximate integral analysis of the boundary layer. And finally, we will learn how to use the analogy between the momentum and heat transfer. In addition to these 4 different methods to calculate the convective heat transfer coefficient, we will see in the next lecture that we can also use different empirical equations to make an estimation of the H value. If you remember from the first lecture when we defined the fundamentals of heat transfer, we described the Newton's law of cooling, which is expressed by this equation here. The heat rate is equal to the convective heat transfer coefficient times the area times the difference between the surface and the fluid that is surrounding this body. In this table here, there are some ranges of values of the convective heat transfer coefficient. You can see, for instance, how the still air has a lower heat transfer coefficient than the moving air. That is, the natural convection usually implies a lower heat transfer coefficient, and therefore the heat transfer or the heat rate is normally lower when it's natural convection. In general, the calculation of H is difficult. It depends on many different conditions, like for instance the mechanism of fluid flow, of the fluid properties, and the geometry of the problem. That's why we will spend some time devoting the study of this H and how can we make an estimation of the H values. In this slide here, there are 4 different processes involving convection. A is forced convection, when we use some kind of device, like a fan, to promote convection. B is a natural convection. C and D, these are 2 situations where, in addition to convection, there is a change of phase. We will learn more about boiling and condensation in lecture 7, I believe. One interesting concept about convection is the windshield temperature, and I'm pretty sure you hear about this concept before. This is just an example of forecast in Buffalo in the winter time, where the real temperature is -7 Fahrenheit, but the windshield, the cold that you feel, is -26 Fahrenheit. So why there is a difference between the real temperature and the temperature that you feel? And this is related to convection. When it's windy, the air that is surrounding us flows at a certain velocity. It's forced convection. The heat transfer coefficient is higher than when there is no wind, and therefore the heat transfer is promoted. So the heat that is leaving our body is it's on a higher rate than when there is no wind. So that's why we feel like it's minus 26 Fahrenheit instead of minus 7. The way to calculate this windshield temperature is relatively easy if you know the Newton's equation. So the heat rate is equal to the heat transfer coefficient times the delta T, and that's when you can get this value of the temperature windshield. Let's see now a few parameters that will help us to make an estimation of the heat transfer coefficient. Usually we define a thin layer of fluid that is close to the boundary, and we made the evaluation over the boundary of the body. Conduction will always be present during convection processes and can play a significant role in any convection process. If we make an evaluation of the heat rate over this surface here, it's clear that the heat that is being leaving or releasing due to convection, this heat here comes from the conduction through the body. So that's why conduction will always be present. Actually, if we do an evaluation exactly over the boundary, over the surface, as I mentioned, the heat that is being released is equal to the heat that reaches that external surface through conduction. The convection equation is this one, the Newton's law of cooling. And the conduction, we can use this expression here to calculate the heat that is getting to the surface, which is equal to the thermal conductivity, the area, and d over dy delta T, and is evaluated when y is equal to 0, exactly the surface. As I mentioned, the heat that is being released by convection needs to be the same as the heat that reaches this point through conduction. So we can say that these two expressions are the same, evaluated over the surface. This is exactly what is this. We play around with this equation here, the areas cancel. So we can get that the H coefficient over the thermal conductivity is equal to the dy, that the delta T evaluated over this surface when y is equal to 0, times the temperature of the surface minus the temperature infinity. If we multiply by the length, we can make this expression here a dimensionless. And this is what we define as the Nusselt number. So this Nusselt number is equal to dy evaluated at y equal to 0 of the temperature of the body minus temperature over the temperature of the body minus T infinity over the length. If we take a closer look to the meaning of this Nusselt number, it's very interesting that we can assume that this Nusselt number is the ratio between the conductive resistance, which is L over the thermal conductivity, over the convective resistance, 1 over H. So the Nusselt number is the ratio between the internal resistance and the external resistance, between the conductive resistance and the convective resistance. In order to define other significant parameters, we will take a look to the molecular diffusivities of momentum and energy. The momentum diffusivity was defined in CE 317 and is equal to the viscosity times over the density. On the other hand, we saw in previous classes that the thermal diffusivity alpha is equal to the thermal conductivity times the density times the thermal capacity. If we also notice that these two diffusivities have the same units. So if we divide the momentum diffusivity and the thermal diffusivity, which is here, this is what we call as the Prandtl number. And again, is the momentum diffusivity over the thermal diffusivity. The Prandtl number is all the parameters here are properties that only depends basically on the temperature. So in most of the cases, this Prandtl number is tabulated, and you can find the different values of the Prandtl number related to the temperature in the Appendix I in your textbook. So we learned that we can define the Nusselt number as the convective heat transfer times the length over the thermal conductivity. And on the other hand, the Prandtl number is a function of the properties of the material, and this is equal to the thermal capacity times viscosity over the thermal conductivity. These two parameters are critical to study the heat transfer coefficient. So let's begin with the dimensional analysis of convective heat transfer. In order to be useful, this dimensional analysis requires experimental results. But we're going to go through the theory of this dimensional analysis, and we will define some parameters that we'll later use for the empirical equations. If we follow the methodology defined by Buckingham when we studied the momentum transfer in CE 317, you can take a look to the chapter 11 in your textbook if you want to refresh your memory. We define the Reynolds number as the dimension times the velocity times the density over the viscosity, and the Prandtl number as well that we just defined a couple of minutes ago. Then for forced convection, we defined the Nusselt number and the Stanton number. The Stanton number is equal to the heat transfer coefficient times the density, the velocity, and the thermal conductivity. So the dimensional analysis tells us that the Nusselt number is function of the Reynolds and the Prandtl number, or equivalently that the Stanton number is equal to or is a function of the Reynolds number and the Prandtl number. In the case of the natural convection, instead of using the Reynolds number, we define a new dimensionless number which is called Grasov. This Grasov number, you have the expression here. I will tell you more about this Grasov number in a minute. What about if we do an analysis of the boundary layer?